Welcome everyone to Support Vectors and to our interesting session today. We are going to have a 3-session, a beginner's introduction to data wrangling with Python. This is, again, a course we are very excited to offer. We tend to offer this course every year, and we feel it's a good warm-up for some of the workshops and boot camps that are upcoming. So those of you who are planning to take our boot camps, etc., of course, you'll find that it is very useful. The topic in and of itself is very useful. Data is everywhere. The scientific world is the world of data, empirical data. Without data, you can't make any definitive statement on any hypothesis. So ability to manipulate the data from its raw forms, and the forms in which data usually comes to us, unfortunately, are terrible. They come with bugs, they come with impartial data. Some fragments of data come from one source, other fragments of data come from other sources. And often you have to create a quilt work of these sources of data to extract that which is of scientific or engineering or practical value. The process of doing that these days, the term people use is data wrangling. So this is a course in data wrangling. We are going to have 3 evening sessions. If you are with me, if you come to the course portal and you go to upcoming courses, you will see 2 tigers wrangling with each other. And that should capture the spirit of our course, because wrangling with data is like that. It takes patience, it takes grit, it takes effort. It's one of those things that whenever you do things like become a data scientist or an AI engineer, you may think that as an AI engineer, or even as an AI researcher, you would be spending the better part of your life dreaming up or conjuring brilliant algorithms. Right? You would create new neural networks, new architectures, new algorithms, you do some mathematical breakthrough. The reality is that most of the time you're wrangling with data, getting data ready to train your AI models. And each AI model needs its own way of data, of training data. Now, data wrangling, of course, bears pretty rich fruits. When you have done the data wrangling correctly, it expedites your scientific journey or your AI modeling or whatever practical use that you want to put to. There is a long tradition of manipulating data. Lord Kevin, there's a long quote of it, but it goes on something like, something has not risen to the level of science until it deals with measurables. And measurables are, of course, data. These days, we shorten it to say Kevin's statement by saying that it is not science if it is not measured, if it is not with data. So data is central. We get data, we live in the data, in a world in which we are inundated with data. We all know these facts, and yet it bears repeating. More data has been produced in the last 2 years than in the entire history of mankind. So all the encyclopedias, all the storage disks, the cloud storages and everything put together, whatever data we have had as of this moment, in the next 2 years, more data than that would be produced. It's a pretty astonishing rate at which data is growing, which again brings about the importance of dealing with data in a powerful way. Otherwise, you are wasting a lot of time when you could be skilled at this and do it well. So I would not venture to say that today's course will make you master athletes with data wrangling, but it will get you started on the journey. If you're not familiar with some of these techniques, and more than techniques, some of the, I would say, principles and ethos with which you should approach data. For example, we'll talk about tidy data. We'll talk about vectorization. These are concepts that underpin good practices or good design patterns with data wrangling. And more than teaching or talking about specific, this is how you do it in pandas, or this is how you do it in Python. You do a join, you do a combine, and so on and so forth. More than that, we would be emphasizing core principles that will hopefully you'll find useful, even though these libraries may come and go. In a few years, you may or may not have NumPy, you may or may not have pandas, but the principles of good data wrangling will hopefully be of good service to you. So with that, I will start with just this course portal. I hope you all are here. If you're not here, please do register. I will give perhaps a couple of minutes to, and I'll talk in terms of generalities rather than delve immediately into the course. This should give you guys some time to get ready with the course, or get ready with the portal. Once you're ready, once you're into the portal, then we will get started. So anybody who is still registering or getting into the portal, please do let me know. Now, what do you find in the portal? You will find in the portal the obvious Zoom link, the Discord server invitation. Any messages that you post, any help requests that you do, we have a teaching faculty of 8 AI engineers and data scientists. These are some of the brightest people. These are people from IITs and with PhDs. These are people who are board toppers. These are, I'm proud to say, this is my wonderful team here at SupportVectors, who all have a passion for teaching, as well as doing research projects. So they are at your beck and call. Post messages, and you'll be pleasantly surprised that we take it seriously. We will help you. And this can continue beyond the 3 days. As you make your way through these exercises in the course of the next week or the week after that, as you have questions, do raise it in the Discord and we will guide you through with that. The next thing I would like to say is there is a zip file here, Jupyter Lab Notebooks. Please download this onto your machine. And then after that, sort of follow along with us. What this particular, because this course, this short course, is data wrangling with Python. Obviously, the prerequisite is you must have a Python environment properly set up. Towards that, we have the first section of this course, which is getting started. I'll go into that section. But before I go into the section, I would also like to mention one thing that's sort of not visible here. In each of the topics, and at this moment, you see that there are 6 topics. In each of the 6 topics, as these topics get covered, like for example, today it would be NumPy and Pandas. As these topics get covered, within a couple of hours, based on what topics, what conversations did take place here, we will post a quiz. When you take the quiz, rest assured that no one is going to see how well you did in the quiz. It is just for self-evaluation. It is for you to check and validate what you learned, how much of it did you grasp. If you don't do well in a quiz, go review it and come back again and take it. And you can keep taking the quiz as many times as you wish. So those are the things here. Now, let's go to the Get Started part. When you go to the Get Started part, you will notice that shoes are perhaps the first thing we put on our journey. So an apt picture. So first thing is you must have Visual Studio Code set up on your machine. You can download the Visual Studio Code. Here is a link to the Visual Studio Code download. Please go and download this. Once you do that, you should install 2 extensions. One is an extension for Jupyter Notebook. Now, Jupyter is spelled in a peculiar way. It is Jupyter. And the reason that it is there, Jupyter, is interesting. Jupyter Notebook aspired to be the data science notebook, the machine learning notebook, uniting 3 different worlds or 3 different languages in which data scientists do their analysis. Julia, Python, and R. And therefore, Julia, Python, R, Jupyter. That's where the word Jupyter comes from. Python is, of course, the language of choice for our sessions. And as you will notice that in the world of Python, snakes are all around us. We haven't even started speaking of Python, and anaconda has showed up. And then lots of animals show up. It's sort of part of the tribal culture in Python to have all sorts of projects named after animals, especially snakes and reptiles. So we will talk about all of these things in due course of time. But what I would request is that if you have not, please download this or follow through with the instructions and take a few minutes. I will just move ahead. We will give you time to do this setup after we talk about the first topic, which is something called NumPy. Right? So let us spark the setup of the environment. If you already have the environment, congratulations. If you don't have the environment, then it will take you time. Once again, remember, on the Discord, and let's use the Discord for discussions rather than the Zoom chat, because my team will get confused. Moving back and forth. To emphasize that point, a Discord link is right here in the course portal. If you go here, you will see a Discord invite. Please accept that invite, and you will be in there. Right? So our team will take you through in the break. We'll have a practical break in which you can reach out to the team, and one of our teaching staff, teaching faculty will work with you closely and respond to your questions. So the first topic I would like to talk about is NumPy. So today, when we talk about data science, the term data science is of a much more recent coinage. But data itself, and therefore data analysis, is as old as science itself. And science is perhaps as old as humanity itself. We can go back and in archaeological findings see our ancestors making markings on bones and doing their data gathering with notches on sticks. So it's been a long journey. Along this journey, though, as the field matured more and more and computers came about, lots of libraries came. The first use, the word computer itself signifies that it was a machine whose primary use was to compute with numbers. And therefore, the earliest utilization of computers was to do a lot of scientific computations. So people created libraries. One of the older libraries that people created way back when Fortran was a dominant language. Fortran, by the way, many people have prematurely mourned the demise of Fortran. Fortran is by no means dead. The scientific community is still heavily reliant on Fortran. But Fortran is the language in which much of the scientific community wrote its scientific routines. Those routines were things like BLAS, LAPACK. BLAS is the basic linear algebra subprograms. LAPACK, which is the linear algebra package, LinPack, etc., and Atlas, and so on and so forth. And then Fortran and C, then came C. There was a time when people worried if C would be fast enough because Fortran is so blazing fast. Right? Then came C++, similar conversations came about. Today, despite popular belief, most of the machine learning libraries, most of the AI libraries, most of the data manipulation libraries actually are still written in Fortran, C, and C++. Right? If you think of these famous libraries like PyTorch or TensorFlow, they are written actually in C, C++. If you think of the libraries that we will be using for this course, NumPy, it has the word pi at the end of it, signifying it's a Python library. But actually, its roots are in Fortran libraries that people have been developing over decades. Why would we use some ancient libraries? It's a question that often comes. In anything else, for example, if you do web development, it is customary to wipe out whatever the previous generation has done. Forget previous generation. Every few years, you say, well, it's time to create a new, modern, better library. Right? So there comes something. For example, came struts and it left. Came Java Server Faces and left. The ASP, active server pages, and is gone. PHP, still dominant, but not many people are too excited about building a new career on PHP, right? And Perl, and so on and so forth. And then you have all sorts of things. And now React seems to be the king of the hill, right? And enough for React. Now people are already thinking of a world post-React, dreaming up libraries that would wipe it out. It happens with languages too. Data science itself has gone from Fortran, C, C++, which is the domain of scientists and researchers, to more popular, more democratized languages like Mathematica, right? And then statistical libraries, SAS. Then came R, an open source library, very popular, made the syntax very, very simple. And then these days, Python. And now there seems to be a movement. Python and Julia are there, and there seems to be a movement towards Rust. For all we know, this year, maybe the last year, we are perhaps at SupportVectors teaching this course with Python. Who knows? Maybe next year we'll be doing it with Rust. So languages come and go, but the question remains, why, now that we are using NumPy, why is it that the scientific routines are still written in Fortran, in C, C++? Isn't it time to move past them? And the answer to that is interesting. It turns out that very basic things are very difficult to get bug-free. If I were to ask you, how would you do the average of two numbers, X and Y, you would say, well, that's very easy. I would do X plus Y, and then I would divide it by 2. That's how you would do it, isn't it? If I were to ask you to take an average of a list of numbers, you'd say, well, very simple, sum it up, divide by n, divide by the length of the list. Common sense. Except that common sense doesn't work in the numerical domain. There are too many subtleties, too many pitfalls. Actually, if you were to do the path that I took you on, it would be a recipe for disaster. And I would leave it to you to discover why what I just said, or what is completely intuitive, doesn't work. Let us see what discussions show up on our Discord channel. And I would also challenge you to come up with the right way of finding the average of, let's say, a bunch of numbers. How would you do that correctly? What are the ways to do that? It is not as obvious as you think. Let us see if we can figure out why it is not so obvious. That's intriguing, isn't it? I'm saying something as common sense as adding a few numbers and dividing it by the count to get the average can get you into trouble. You have to use different ways. And so those different ways emerged after years of, getting burnt and having bugs. So these scientific routines have evolved with a lot of battle testing. These are the routines, by the way, that do your ocean current dynamics. These are the routines that make your weather predictions. These are the routines that send a man to the moon or a spaceship to Mars. And these are the routines that are there in every space exploration, in the simulation of the hydrodynamics of a nuclear fission or fusion, and name it. All enormous scientific enterprise use these libraries. So you don't want to replace these libraries and start all over again and say, let me start from scratch. Because if you do start from scratch, as the saying goes, they who forget history are forced to repeat it. You'll repeat every single bug, or most of it, because you wouldn't know that these traps are waiting, these landmines are waiting for you. So NumPy as a library, actually, as a starting library, I would say, is a library that does not reinvent the wheel. First, Python is an extremely slow language. It's an interpreted language. It's not a disparaging statement about Python. Python was designed to be interpreted. It was designed to be dynamic, intuitive, and it has served that purpose very well. It was never designed to be lightning fast and close to the bare metal. For that, there are languages like Fortran. And so NumPy is a library that whose great claim to fame or main purpose of what's the word raison d'etre is that it democratizes those libraries and makes it easily accessible in Python. It says you can have all the speed of Fortran and C, right? And all the utter reliability, the decades of reliability, computational reliability of those libraries. Nevertheless, you can have a very intuitive syntax, even more intuitive than Python itself, surprisingly. And we will see that in a few moments. And that is the crowning achievement that NumPy brings to the table for data manipulation. Remember, if you have data, you will have rows of data, you'll have matrices of data, tables of data, which are matrices. Or you'll have multidimensional tables of data, which are tensors. NumPy is a library that gives you two things. It gives you a very, very, very intuitive syntax for dealing with arrays, multidimensional arrays. The word is multidimensional. Whether you think of one-dimensional array, you think of a matrix, you think of a tensor. These are n-dimensional arrays, and NumPy gives you a syntax that just core Python, it beats core Python in intuitiveness, and that is saying something. So that is the first thing that it gives you. The second thing it gives you is, it says, while you are having a very intuitive syntax, there is no compromise on speed. Anyway, because what you're doing is, you're doing vectorized computation. You're not doing it in Python. You're instead you're pushing it down to the core numerical libraries that have aged well and become bug-free or nearly bug-free after years of testing and years of utilization. So that is the main thing that NumPy brings to you. And so let us go and see what NumPy does. In the course portal, I put a few links for you here. One of them is to the NumPy portal. Let's go there. If you go to this portal, NumPy is in 2.0 release. It has lots of utilizations. If you see, there is a lot going on here in this, but I would suggest go to the documentation. And in the documentation, go to the absolute beginner's guide and start from here. And you will get a pretty good sense of what NumPy can and cannot do. Now, while you can do that on your own, today I'll take you through a little bit simplified and hopefully a more intuitive journey through NumPy. So let's go through that, and hopefully I can convince you of this logo is huge. All right. Why NumPy? Right. We talked about that, but we will see its value through a few examples. Let's take something very simple. Suppose you have a rectangle. It has a length, it has a width, and you want to find the area of the rectangle. As any elementary school kid will tell you, the area of a rectangle of a rectangular plot is length times width. Let us make it more real. Suppose you're looking at plots of land. Right? Now, area is length times width, and we write that here. Area is length times width. Then you go on and say, all right, what about the perimeter? Perimeter is the number of, or the distance you would travel if you walked around the periphery of the rectangle. So the perimeter is 2 times the length plus width, because twice you'll go along the length side and twice you'll have to go along the width side. Let's try to do it in normal Python. If you had one box, one plot of land, you would say, let's for the sake of argument, say length is 3 and width is 5. So the area is length times width. A perimeter is this. So area is 15, perimeter is this. But now let us say that you don't get one instance of a rectangle, but you get a list of rectangles. There are 5 rectangles. For each of them, you get the lengths. So the first array, the Python list, is the length of each of the 5 rectangles. And the width, this is the width of those rectangles. So think of 5 plots of land that you happen to have measured. If I were to ask you, what is the total area that you have? You would say, well, what I have to do is multiply each of the length, in the length record, each of the items, let's say 5 with 3, and 2 with 2, and 7 with 5. And you say, well, that's easy. Why not go do it? And those of you who are Pythonic, who are gurus of Python, to do that, you would be doing something like this. This is actually a pretty complicated code, right? It is not intuitive at all. If you just did length times width, do that, and you would be in for a surprise. I'll leave that surprise to you. Try that. Try this bit, right? What would happen if you just did area is length times width? And it's fun to do that, you know. So what you find is, despite the intuitiveness of Python, and Python is certainly a very intuitive language, nevertheless, for mathematical things, it doesn't quite work as well. Likewise, if you try to do the perimeter, 2 times length plus width, what you will end up with is instead this. Right? This is not what you would expect. What it has done is, it has, when you do 2 times an array, it just goes and repeats the array. You notice that this part of the array is being repeated in the right-hand part of the array. Right? So obviously Python's way of thinking, intuitive it may be, but it's certainly not how mathematicians think, how data scientists think. Right? So what you need is something different, right? What can we do then? To get the results, now you can write your own code. You can write a code. You'll have to write a code very similar to this code. I'll leave that as an exercise for you folks. And you can get it right. There's nothing. You will have to just say X perimeter. You'll have to go about adding 2 times X plus Y and so forth. Zip, a very small modification will give you the answer. Having gone through this arduous journey, now you say, oh, well, surely we should have a library in which we can do our computes as intuitively as we write our basic algebraic equations. Wouldn't it be nice to have a library which makes it almost that easy to do it? And such a library is indeed NumPy. And let's try to do the NumPy way. How would you do it with NumPy? First thing is that you can give the old arrays, or you could have created those arrays natively in NumPy. But at this moment, since we have created those length and width lists in Python, we'll just convert it to a NumPy array. Any list can be converted to a NumPy array with the np.array. By the way, this is almost a de facto mantra. Whenever you import NumPy, you do it as np. Right? And if you want to confuse your friends, then say import NumPy as PD, pandas or something like that. No, I'm kidding. So this is a universal convention in the field, right? Don't sort of diverge from this. You converted them into this, and now see what happens. When you say area is NumPy length times NumPy width, and perimeter is this, look at this. Does this look and feel dead intuitive, guys? It feels exactly the way you would write your math, isn't it? Right. And then when you print it out, you get the results that you want. So what are the observations from this bit of code? The code feels more native to numerical computation somehow. The other important thing is we are not doing element-wise operation. When you use the zip and the list comprehension, like this is using zip and list comprehension, the pure Pythonic way. Where are we? Oh, we have gone past it. Yeah. Yes. When we do it like this, this is called, in Python, we call it list comprehension. And this is it involves a zip function between two, because you are zipping through, as in the physical zipper, zipping through the elements of the two array. You're not doing the NumPy way. You're not doing element-wise I apologize for the typo here. Operations. What you say or the verbiage that people use in our field is you're doing vectorized computations. Means you have converted into a vector, or the unstated thing is these vectors actually exist at the level, at a much lower level, at the level of Fortran/C. Right? And you're directly manipulating vectors because those libraries are extremely good in doing vector computations. They can do a dot product between two vectors, literally as in parallel, like literally as just one go at it. They can go at it. These operations are pushed down at the BLAS and LINPACK layers. So it makes it blazing fast. So you get the best of both the worlds. You get a very intuitive feel, right, to what you're doing. At the same time, you gain speed. You gain much faster computations. So if you were to compare the execution time, and here is a bit of code that will compute the execution time. Let us see. The execution time is, if you look in terms of microseconds, I believe this is, what is it, 28 milliseconds? Yeah. 28 milliseconds, 28.6. And compare it to the way NumPy does it, it's 4 milliseconds. Actually, the performance gain is not just this much. When you have large arrays and compute like multidimensional arrays, this overhead is mostly the overhead of pushing it down to the lower layers. Right? The actual computation at the level of Fortran and C are much, much faster. Right? Native computes are very, very fast. So that is one thing to know about NumPy. Now, what about other operations? It turns out that the operations with NumPy are actually very intuitive. Let's look at that. If you want to take a subset, for example, you want to get the first element of the array, you can do that. But what is very odd is if you take an array, NumPy array, and you say, give me all of those elements where the area is greater than 30, it will actually tell you which of these elements fulfill that condition. Do you see that? This is very, very interesting because NumPy has overloaded this definition of greater than in such a way that it makes it intuitive. It makes it very intuitive. And if you want to just say, okay, don't tell me that it is yes, it is greater than 30, it's no, it's not, or false, it's not. Instead, just give me that subset of plots of area which are greater than 30. So you can just say area, and in between, you can give your Boolean condition, right? So you're not just indexing, you're giving it a condition. And the moment you do the condition, it works. It also gives you a lot of convenience methods. For example, given two lists. Now look at this list. These are non-homogeneous lists. They are elements which are numbers. They are elements which are Booleans. You can actually do a sum of these. It will treat true as 1, false as 0, and it will give you the addition. Right? You can deal with two-dimensional arrays, nothing unusual here. You can convert two-dimensional numbers as arrays, and you can do multiplications, you can do all sorts of operations and indices. More than that, you can do statistics on the arrays. Suppose you take a whole lot of numbers, you can check its shape. By the way, taking an array, you often forget what was the shape of the array, how many dimensions were there, how many rows, how many columns. You can always recall that by asking the NumPy array to declare its shape, and it will declare its shape. Right? You could do all sorts of things. It comes with a lot of statistical measures come built in NP. So if you go to the NumPy library, you will find close to 200 or more functions present. Most things that you encounter in your high school and in your college mathematics courses, they have all been simplified down to a single function in NumPy. So as you can imagine, this library is very, very powerful for data analysis. Right? I would strongly encourage you to become familiar with NumPy, but becoming familiar with NumPy is not a feat for a day, right? As they say, Rome wasn't built in a day. your mastery of NumPy is like that. You have to take it up in small bites. So that's that. As the kid's joke goes, how do you eat an elephant? Bite by bite. Right? So you have to every day or as you become familiar with NumPy, every day go pick some functions, see what they do, practice it, and gradually you'll become good at it. Actually, no one can remember all the functions. I probably remember 2-3 dozen of them. I know they exist. If somebody points out, I'll recall, yes, I know it's there. But off the top of my head, if I were asked to enumerate the functions in NumPy, I would probably not be able to go beyond 3 dozen. If that. So you do it on a need to know basis. All you need to know is that if it is standard mathematics, it's probably there already in NumPy. You don't have to reinvent the wheel, right? So I asked this question, how do you find the mean of numbers? I'll let you figure out. How does NumPy do it? So NumPy array, you can do all sorts of mathematics. One of the interesting things is, while a typical programming way is if you get 2 arrays and you want to add those, you could do np.add. It's very function way of doing it. There's an add function, but you could just give the plus symbol, minus symbol, multiplication symbol, divide symbol. These symbols are all supported directly in NumPy. Anything that you can think of as pure math, you'll find.
It would change X, or it would kind of create another array?
No. It would create another array for you.
Okay.
Right? And it gets even more interesting. You say, well, those things perhaps Python itself has, to some extent. Right? But it gets more interesting when you want to do, for example, a dot product. So when you do a dot product between 2, you can do, well, this is intuitive enough. NumPy has a method called dot, and you can do dot product, inner product between 2 vectors. By the way, what is inner product? It's the projection of one vector onto the other. Right? One vector onto the other. So these are 2 methods that you would have anticipated. But if you're not familiar with NumPy, it comes as a surprise that you can do the dot product between 2 vectors simply with the @ symbol. Right? How very convenient. Machine learning, it would not be too much of an exaggeration to say that, like, you can almost think of it that dot products are, in some sense, the internal combustion engine behind the car that's AI and machine learning. Right? It's everywhere doing the job, doing your things. So dot products are everywhere. Right? People get fancy, and with certain conditions, these are called kernels and whatnot. But we will leave it as that. Transpose is easy. You can do histograms. You can do all sorts of. By the way, I'm just going over it. What's a transpose of a vector or an array? Well, if it is a row vector, make it dangle vertically. If you dangle it vertically, it becomes a transpose of itself. Rows become columns become rows, kind of a thing. Right? So you get all of these things, and given an array, given a multidimensional array, let's say a whole grid matrix, you can do row-wise marginalization, row-wise sum. You can do column-wise sum. You can do also, or you could sum all the numbers in the matrix. So everything is possible. Transpose syntax is beautiful. Just x dot t, capital T for transpose. It also comes with basic, as I said, the statistical capabilities. You have a bunch of numbers. You want to do, for example, normal distribution. Normal is a distribution, bell curve distribution is called normal distribution in statistics. Right? And you can have fun with it. Easily, you can give a mu, where is it located? So mu is 3. So you can see that the center of the bell curve is at 3, give or take. Standard deviation, sigma. So you can see that if I go 0.75 up to here, you get the bulk of the mass of this under this. We are generating 10,000 samples of the data, and then we are saying plot the histogram. Here is the histogram. You're asking it to, like, it will do that. Now, one nice thing about NumPy is people have built a lot of libraries on top of NumPy. two great libraries on top, many great libraries, but two in particular on top. One is Pandas, which is data frame, machine learning or data analysis. The core sort of a representation for it is a data frame. Many of you with a background in data engineering may remember or may have encountered data frame in some other context, let us say Spark or something or the other. The data frame is inherent or is a core concept in all data, sort of a data manipulation language, statistics and data science. Right? So you and Pandas provides you a mature data frame. Kyle is going to go over that shortly. Then there is matplotlib. If you want to do visualization, now it turns out that in Python there are many visualization libraries, but over the years the one baseline library that has remained the most popular library is matplotlib because of its utter simplicity. There are fancier libraries, more interactive libraries like Plotly, like Altair, right, and so on and so forth, built that use alternative ways of data visualization. But it and they all actually have NumPy integrations, or all of them have NumPy integrations, one way or the other. And then the scikit library, which you use to do machine learning with tabular data, the most popular library to do machine learning with tabular data. By the way, that course I'm starting from Monday. So I invite you to be there if you're interested in a very gentle introduction to machine learning. So then in this particular case, you can see you can build a histogram using matplotlib, which has a histogram function. It will do that. You could have computed the histogram using NumPy itself and then given the results over to matplotlib to plot. So there are two different ways that you could have done it. Right? Either way, you look at the two different ways of doing it. So NumPy could do all sorts of everything that common sense. For example, everything that you could do in high school. Trigonometry, well, here's trigonometry. Right? But I invite you to be more adventurous and try more esoteric functions. Go try out beta function, gamma function, like be even more adventurous. Go try out, I don't know, things like Gompertz function, right? And Weibull function and whatnot, log normal functions, all sorts of esoteric functions that you will think of. You will find that there is support for all of that, some directly in NumPy or some in libraries that have been built on top of NumPy, like SciPy. Right? So SciPy is a scientific computation library. Between them, they will probably have you covered completely. They'll give you most of the functions that you can think of, especially the transcendental functions. So with that, I'll take a small pause. Let's take this pause. I'll stop the recording at this moment so that we can take a 20 minutes break. Our goal in this recording is, or sort of in this pause or interval is that you go back to the basics and make sure that your environment is set up and you run this library on your own environment. Make sure that it works. Where are we? We go back to the course portal and in the getting started, you follow all the steps. We will take a 15-minute break and then after that, I'll hand it over to Kyle to take the rest of the sessions forward. So a word on Kyle. Kyle is one of our bright, she started here at SupportVectors. She actually learned machine learning at SupportVectors many years ago. She's a India board, there's something called board exams in India, and she's a board topper and an architect in multiple ways. She's a software architect, and while she was at it, she's also a real architect, real world architect. And she's our AI engineer, and I'm sure she will help architect your expertise in data analysis going forward. So with that, I will stop the recording and later on we'll restart a new recording when Kyle stops. It is 8 o'clock here. We'll start at 8:15. So please do follow the getting started instructions and we'll take it up from there.